What is the structure of this? Is actually, I said yesterday, I said the coordination number is 6, right? But the coordination number varies. What are some coordination numbers that you recall from Chem 1A? What's the highest coordination number that you can remember? 12, yeah. 12 was one of the highest coordination numbers. That was for cubic closest packed and hexagonal closest packed. So this is the closest packed in the sphere. So each sphere is actually bonded to 12 other spheres. For cobalt, I said just in our drawing, you could coordinate it with 6. 4 in the plane, 1 on top, 1 below. But the actual crystal structure depends on how those ions are packed together. And so yesterday we're going and reviewing some Chem 1A topics. Go ahead and grab. And so one of the Chem 1A topics that we're talking are the types of solids. What types of solids are there? So we go down the list. Metallic solids we're going to talk about later. But the coordination number that you saw, 12, that was for a metallic solid. Gold. Gold has a coordination number of 12, and the bonding isn't very directional. So gold is very malleable. It's ductile because you can displace those 12 atoms, and tweak them a little bit, and so that gives its properties. We have ionic, right? We have network covalent, and we have molecular. Now, molecular solids are a bit different because they aren't held together by actual bonds. They're held together by IMFs. And so the IMFs, we have different types of IMFs. For nonpolar, like oils, what holds the oil molecules together? Dispersion forces. And so nonpolar, the only force is dispersion. Sometimes the dispersion can be quite weak for small molecules, or they can be quite strong for big molecules. Like, for example, wax. Wax has big hydrocarbon molecules in there, and the melting point of wax is fairly high. Or asphalt. Asphalt is a mixture of nonpolar hydrocarbons, and in order to melt asphalt, it takes very high temperatures. And so these can be weak to strong, but for small molecules they're weak. Polar a little stronger for small molecules. So we have polar, and we have hydrogen bonded materials. But even, a lot of people think, well, the hydrogen bond is, one of the stronger intermolecular forces. But how strong is a hydrogen bond? How much energy does it take to break a hydrogen bond? Do you say a little bit of energy or a lot of energy? A lot. And so about how much is that? Roughly. About that much? Okay, if a hydrogen bond was this much, then what is a covalent bond? That much?
Sure.
Smaller? A covalent bond is smaller? Covalent bonds are weaker than hydrogen bonds? Yes? John? Hydrogen bonds, well, actually, these are IMFs. IMFs are typically weaker than the actual bonds. And so one of the stronger IMFs is a hydrogen bond. That's about 25 kilojoules per mole, just as a reference point. So if we have 25 kilojoules per mole to break a hydrogen bond, how much energy does it take to break a covalent or an ionic bond? A lot more, because that's an actual bond rather than an IMF. And this gives their characteristics. Molecular solids are soft. It's easy to break the intermolecular forces that hold the molecules together. And so it's soft. They have low melting point, etc. So they're going to have certain characteristics that are associated with being molecular solids. Now, when we go to network covalent solids, network covalent solids are very hard, and they melt at extremely high temperatures. They could also vaporize. they might skip the melting process altogether and do sublimation. Most are non-conductors. And so this tells me the bonds holding the atoms together in a network covalent are quite strong. It requires a lot of energy to break. And so, well, what's a typical covalent bond? How many? If I said 10,000 kilojoules per mole, does it sound about right? Or maybe it's a million? Is it a million kilojoules per mole? So if a hydrogen bond is 25 kilojoules per mole, then a covalent bond, 25,000? What sounds about right? And so what you want to do, it's easy to forget these numbers because you don't use the numbers very often, but once in a while you want to remind yourself of the numbers. And so what are the typical bond energies for a covalent bond? What's a weak covalent bond? What's a strong covalent bond? And so, so let's just refresh. This is from chapter 10. And so we look, when you look at a table like this, there are just a whole bunch of numbers. So it's easy just to forget it, just a bunch of numbers. And, a lot of people have asked me, oh, should I memorize this chart? Should I memorize these numbers? And I think, no, you don't really need to memorize these numbers. But you want to memorize a couple of things. What types of things would you like to have memorized? Just ballpark. What you want to memorize is not necessarily the individual numbers, but what you want to memorize is maybe the extremes, what the low and what the high is, the extremes. Like, you already do this. So, for example, if somebody told you that, oh boy, it was so hot yesterday, it was like 100 degrees Celsius. What would you say? You'd say that's ridiculous, right? 100 degrees Celsius. What were you, in a pot of boiling water? Oh no, I meant 100 degrees Fahrenheit. But you want to know how many people say ridiculous things to me? They say ridiculous things because they write ridiculous numbers on their tests, and I go, where did you come up with this number? Because that number is so far out in space that it's clear that you have no clue or concept of what is an acceptable range. But that's the problem all of us have, because all of us, what are some reasonable numbers? And we all get trapped in this because we don't know all the numbers. But what you want to do is you want to start thinking. When you get a chart like this, you can see. Do you see any like 10,000 kilojoule per mole bond energies? And so if somebody said, well, I calculated the bond energy, the carbon-carbon single bond energy of 10,000 kilojoules per mole, you might go, oh, that just doesn't sound right, does it? But a lot of people, they say, oh, okay, because they don't have a clue where the range is. Well, think about, what is the range here? What do you see as the range? Yeah, about 150. Actually, here, 142 is the weakest. You know what kind of bond this is? This is a special bond. This is called a peroxide bond. Peroxides are inherently unstable. A lot of peroxides are quite explosive because they're so unstable. But this bond is quite weak at 142. You think visible light will break that? Will visible light break 142 kilojoules? Well, it depends. How many kilojoules per mole is visible light? Like if I took a red photon, is a red photon more, would you guess, or less than 142 kilojoules per mole? Well, how about a violet photon? What would you guess? And so, we want some kind of, I don't mean to say, like we memorize things just, like a table like this with a bunch of random numbers and you just memorize it, 398, 402, whatever. And no, we don't want to memorize things in that way. What we do is we use a combination. We use a combination of some memorization with some theory. And that combination, it's not always theory too. Sometimes it's just patterns because the theory isn't all there yet. And so here, when we look at this, we look at the range, 142. Yeah, hydrogen peroxide. You know, they store hydrogen peroxide in brown bottles. They don't use transparent bottles. Are you doing why? To protect it from light. Have you ever looked at a bottle of iodine? Like betadine or something like that? Is it in a transparent bottle or is it in a brown bottle? It's in a brown bottle. Why? Because light's going to break the bond. We don't want that to happen. And so certain things, these bond energies are quite weak, and these bonds can easily be broken by visible light. Other things, though, you can store in transparent to visible light bottles, that is clear bottles, and not worry about it. For example, nitrogen gas. Do you think you're going to break this bond in nitrogen gas with visible light? No, in fact, this bond is so strong, this is at the high, right? And so it varies. We'll just say it varies from about 100 to 1,000. Okay, so we see the variation between 100 and 1,000 kilojoules per mole. This is what I do for tables, and a lot of, I used to not pay attention to tables because I thought, yeah, there's a bunch of numbers, there's no way I'm going to memorize that and remember it. Right, but there's certain things that you can do that'll help you, and then you look for patterns. What are some of the patterns that you see here? And the patterns that you see, you kind of look. Most of the single bonds are around what? You say 200? Would you say most of the single bonds are around 200? I'd say a little higher. Take a look at all those single bonds and kind of give a rough average. Yeah, most of the single bonds are around. Yeah, around 400, wouldn't you say? 300 to 400 kilojoules per mole. And so and then the double bonds are about what? So let's just say, because there are some 400, 600, and then the triple bonds are 900, 1,000. And so you just keep it simple. Single bonds are around 400, double bonds are around 700, and triple bonds are around 9,000. Just keep the numbers simple so you have some kind of ballpark figures. This is what you can do with certain tables. Rather than memorizing numbers, we kind of just memorize a pattern that's associated with that, and then we can use that pattern to make simple predictions. It's not going to be totally accurate, so we got to worry about certain things. All right, so network covalent solids. Now, how does that compare? What was a hydrogen bond interaction? Hydrogen bond interaction was around how many kilojoules per mole? This is ballpark. They're a lot weaker. 100 to 200? Yeah, that's a good guess. I mean, weaker, so that wouldn't be too far terribly off. But they're quite a bit weaker than this. I'd expect a hydrogen bonding interaction to be a lot weaker than an iodine-iodine covalent bond. Yeah, something like that, more like 0 to 100, But let me just tell you, it's around 25 kilojoules per mole for a hydrogen bonding interaction. So around 25 kilojoules per mole is quite a bit weaker than all these. And so you can see network covalents are going to be much harder because they're covalent bonds. Although these are all these are molecules here, not necessarily. We're just looking ballpark what covalent bonds are. And so in diamond has a whole bunch of sp3 carbons. They're all covalently bonded like this. It's 347 kilojoules per mole to break. There's a lot more energy than it takes to break a hydrogen bond. interaction. And so that brings us to ionic. What is this? Is this network covalent here? Is this molecular? I mean, maybe it's molecular. Did we talk about this already? Yeah, is this molecular? No. How do we know? Because typically metals and nonmetals make ionic compounds, so that would be our best guess. And so we'd say this is ionic. Now I'm going to ask you, are ionic bonds stronger or weaker than covalent bonds? Stronger? Or weaker. Okay, so think of a network covalent like quartz. You know, if you have a quartz crystal, that's a network covalent. Or diamond. Diamond's network covalent. And so the bonds in diamond are weaker than the bonds in, let's say, table salt, which is a ionic solid. That attraction is so strong that we call it an ionic bond. Yeah, you're right. That's absolutely right. It has to do with the degree of the attraction in how we classify it. Because in chemistry, the attractions are all the same. You know, whether it's a covalent bond, ionic bond, hydrogen bond, you know, intermolecular force, the attraction is what type of attraction?
Electrostatic.
Oh yeah, electrostatic or electrical attraction, right? It's just positive being attracted to negative. Now the reason why a dipole attraction is a lot weaker than, let's say, an ionic bond is because it's just partially charged rather than fully charged. But that brings up the point, you know, what are the bond energies for an ionic solid? So let's go ahead and first let's write out the structure. What is the structure, the Lewis structure of this? And so we said that this Lewis structure is wrong. I assume that this Lewis structure is wrong because this should be a ionic compound, and ionic compounds don't form molecules like this. And so what is the Lewis structure of cobalt-3 chloride? Did I already write this on the board? Oh, okay. Okay, this is where you're telling me about, and this is where I said the coordination. When I write it like this, the coordination number looks like it's 6 because I can easily fit 4 chlorides around this in the plane, and then I'll put 1 on top and 1 underneath, and that gives me an octahedral coordination of chlorides. And this is just an electrical attraction, like you mentioned. And we don't show it, but this is an actual bond. You know, it's so strong that we call it a bond. Now, if I'm looking at this, then each chloride will want to surround itself with as many cobalts, and each cobalt will want to surround itself with as many chlorides. And depending on the size of the ions, that's going to dictate what the coordination number is. You know, for example, if the cobalt's very small, or the cobalt's very big, and the chloride as well. And so we have something called the radius ratio. Have you ever heard of the radius ratio? Radius ratio is something that helps us predict what the packing arrangement is going to be, depending on the ratio of the size of the anion to the cation, or the cation to the anion. And so you have different radius ratios, which will give you different structures. So for example, this radius ratio prefers to be in this type of structure. You know, big cation, small anion. Big anion, small cation prefers to be in a different structure, depending on how they pack together. That's for spherical ions. And then you have non-spherical ions. You know, you have ions like carbonate. What shape is the carbonate ion? The carbonate ion is trigonoplanar, and so that packs together a little differently. Acetates are even more complicated in terms of their shape. And so we got to look at, you know, the shapes of the ions and the size, and then we can figure out how they're going to pack. And so the reason I drew it like this with a coordination number of 6 is just to illustrate that ionic compounds form, what's this structure called? Well, this is the Lewis structure, but what is, when I extend it out like this, what's that called? A lattice. And so ionic compounds form a lattice of alternating ions. And, whatever pattern that ends up being, there's certain things that can help us predict, but we aren't going to be at that level of predicting the particular structures. And so we can see some structures here. This is the structure of zinc sulfide. You can see how the ions pack together. Calcium fluoride, titanium fluoroxide. This one is not cubic. This is orthorhombic here. It has a rectangular cube rather than a cube. I picked sodium chloride because sodium chloride is a very common structure. A lot of salts adopt this structure here. This is called the rock salt lattice, in which you can see how it packs together here. And if you look at the coordination numbers here, all the greens are coordinated to 6 purples, and all the purples are coordinated to 6 greens. So it's just a simple packing arrangement of this. Another way of thinking about this lattice is it's a face-centered cubic arrangement of green spheres with the purple spheres in what type of hole? Well, the type of hole here is an octahedral hole. Octahedral holes are 6 coordinate holes. Well, anyway, that's was so. I don't. We could easily look up the crystal structure of this. This is pretty common, but I'm not. It's just going to pack together in some arrangement. We can determine it experimentally using X-ray crystallography and figure out the packing arrangement. But as a crude general depiction of what this lattice is, it's like this. Okay, so this will be cobalt 3 chloride. Now, the bonds are pretty strong here. So that's the solid. How strong are ionic bonds? Well, that wasn't a fair question. Because what we're going to see is that, covalent bonds span a pretty big range, from 100 to 1,000, right? What's the range for ionic bonds that you've seen? Well, this is why I like to do, when I was a student, and I still do this, but if you spend 1 hour on one homework problem, that's like, it's like, let's say you're in a big forest, and you're just looking at one tree, and you're going to spend 1 hour looking at that tree, and then you run out of time. And so you know that tree pretty well, right? But you don't really know the expanse of the forest, right? You don't know the limits, where it starts, where it ends. You don't know the elevation changes. You really don't know the forest, basically, wouldn't you say? If you spent all your time looking at one tree. And so my analogy to this is, this is like the homework. Do every single homework problem. If you do every single homework problem, then you'll see the expanse of the forest. Right? You'll see the limits. Although our homework sets aren't totally comprehensive, they'll give you a better idea. And so if you go back to, and I didn't have enough time to talk about the Born-Haber cycle in detail. But you could use Hess's law to determine the lattice energy of sodium chloride, because the lattice energy of something like sodium chloride, if I have 1 mole of sodium chloride, how many sodium chloride bonds do I have to break? If I have 1 mole of sodium chloride, do I break 1 mole of sodium chloride bonds? Yes? Did I already ask you this? Yeah. Do we break 6 moles of sodium chloride bonds? Because the coordination number is 6. No. We have to break a A lattice. Now, what is a lattice of bonds? Did I talk about this? No. Okay, let me tell you what a lattice of bonds is. Since chemistry, deals with electrical attractions, and that's all chemistry is, electrical attractions, then we're going to look at it like this. This cobalt, if I look at this, is bonded to what we call 4 nearest neighbors. And then if I look at the next nearest neighbor, is it going to be attracted to the next nearest neighbor or repelled? It's going to be repelled. And so these next nearest neighbors are repulsions, but the next nearest neighbor is an attraction. And so that'll be here. An attraction. And so what I do in order to determine the lattice energy is you have to sum up all the attractions over 3 dimensions and subtract from that all the repulsions over 3 dimensions, and then you get what's called the lattice energy. And so it's breaking all the attractions in 1 mole of crystal. Well, in order to do that for sodium chloride, we could use the Born-Haber cycle like this, or Hess's law, and we can calculate it. We don't actually have to measure it. How do you measure delta H's? If you had to measure this, how would you have measured it? Well, how do you measure experimentally delta H's? Thermometer? A calorimeter. And so we don't have to do a calorimetry experiment because all these other values you look up in the book. And so by combining this is called the Born-Haber cycle, and this is why it's famous, we can calculate the lattice energy for sodium chloride. And the lattice energy for sodium chloride turns out to be 787 kilojoules per mole. And so if I had a mole of sodium chloride, I'd have to input 787 kilojoules to break all the attractions holding the ions together. And what I should get molten sodium chloride, but I don't. A lattice energy is defined by as taking the solid, I know it's hidden here, but this is solid sodium chloride, and converting it into the gaseous ions. And so not only is it breaking the ionic bonds, it's also vaporizing the liquid. And so it's actually 2 processes, the fusion plus the vaporization. But anyway, getting back to this, it's still, this is going to be a little bit more energy than just breaking the bonds, because we're also vaporizing. But take a look at the energy. 787 kilojoules tells you what? Is that kind of big? Kind of strong? This is equivalent to what? Yeah, almost a triple bond, but we'll just call it a double. Double to a triple. And so, the lattice is actually quite strong. And so let me ask you one question. One question is, diamond has carbon-carbon single bonds. What was the carbon-carbon single bond roughly? Just ballpark. You don't have to get it right. 150 is about the weakest, but diamond's going to be a lot stronger than that. Visible light's not going to break diamond. Yeah, it's about 350, but ballpark, just say 400, 500, something like that. Is light going to break that bond? No. Does diamond dissolve in water? No. But sodium chloride dissolves in water, doesn't it? In order for sodium chloride to dissolve in water, what do you have to do? Yeah, that pulls them apart. In other words, you have to break apart the lattice to get it to dissolve. And so when you look at this energy and you compare it to diamond, why does sodium chloride dissolve? It costs 787 kilojoules per mole to break the lattice. It's not accurate because of this vaporization, but still we'll just ballpark it. And so let's say it costs 700 to 800 kilojoules per mole to break sodium chloride lattice, and it dissolves, but diamond does not dissolve. Why is that? The bonds are stronger in what? The bonds are stronger in the diamond than sodium chloride? Okay, look at sodium chloride's number. Here's diamond's number, 347. So why is that? It looks like it's easier to break the bonds in diamond. For sure, it costs less energy. It's easier to break the bonds in diamond than it is in sodium chloride.
Just the way they're structured, because the NaCl has a lattice.
Well, diamond also has a lattice. Do you guys remember the diamond lattice? I'll show it to you. This is the diamond lattice. Here, sp3 carbon. So the diamond lattice. The diamond lattice is often thought of as a face-centered cubic arrangement of carbons with carbon atoms in what we call the tetrahedral holes, half the tetrahedral holes. And that's one way of visualizing this structure, so it's easy to remember. You know. But looking at this lattice, I mean, it's got a lattice too. And so lattice in diamond, 347 kilojoules per mole. Lattice in sodium chloride, 787. Which one's easier to break? Diamond. So why doesn't diamond dissolve too? Or opposite, why does sodium chloride dissolve? You know, it shouldn't dissolve if it has a stronger lattice.
Because sodium chloride has an ionic structure. That's why it has both positive charge atoms and negative charge atoms. And water has hydrogen bonds that mean like water has also positive and also negative. So they have like similar connection, or I can say similar attraction.
Yeah, that's exactly. Another way of thinking about it is like oil and water. If you break apart the carbon lattice, you get carbon atoms. Carbon atoms are like oil; they're nonpolar, right? If you break apart the sodium chloride, you get ions. Ions are highly polar, and so we have that rule: like dissolves like, and so that would be similar. It would be. It's not that. It is true, this is easier to break apart, but it forms a highly unfavorable product, oil and water. It doesn't want to happen. Whereas sodium chloride forms a highly favorable product because when you dissolve, and I have this slide too. What chapter was that? Chapter 13. This is what happens when you dissolve an ionic solid. When you dissolve an ionic solid, there are going to be collisions, the water molecules can collide. And what can happen is it can break that. Because do all the water molecules in water move at the same speed? Let's say I have a sample of water, a cup of water at room temperature. If I have a cup of water at room temperature, are all the water molecules moving at the same speed? Yes or no? No, we know that some of the water molecules at room temperature are going to be moving faster. Some of them are going to be moving slower, and we know that there's a distribution associated with that. It's the distribution looks like the gas speed distribution. Do you remember that? That distribution has a name to it. Do you recall the name of the distribution? The thermal distribution. I didn't pull up chapter 6, but it's from chapter 6. Yeah, the Maxwell-Boltzmann distribution. Good. And so we're going to have a Maxwell-Boltzmann distribution of kinetic energies in here, even though this is room temperature. So some of these water molecules have pretty high energy. They hit this, break off an ion. Now this is the key point here, because it's going to be hard to break off the ions here, but what forms is highly favorable. Do you know what this is called? These arrows show an attraction, an electrical attraction. So what type of attraction, intermolecular force, or IMF, is this? Is this a hydrogen bond interaction, a dipole-dipole interaction, or dispersion interaction? What type of interaction is that? It's not a hydrogen bond. It's not a dipole. Everything has dispersion, but that's not the primary thing here. Yeah, there's a right answer, and that is there are more intermolecular forces than those three that I just named off. What is another intermolecular force or IMF? You know what this is called? This is called an ion dipole attraction. And in ion dipole attractions, those can vary from extremely strong to extremely weak. Typically, ion dipole attractions are stronger than hydrogen bonds. Why are ion dipole attractions stronger than hydrogen bonds? Because when you think about hydrogen bonding interactions, you have an unusually large delta plus on the hydrogen atom. So you have an unusually large positive charge density on H being attracted to the negative charge density here. But, you know, even though the positive charge on hydrogen is unusually large, it's still not a full positive charge. This is wrong. They show a full positive. They should have shown a delta positive. A delta positive just means a partial charge. But an ion, is an ion a partial charge or a full charge? It's a full charge, so this is a stronger electrical attraction. And electrical attractions depend on two things. What do they depend on? Electrical. You know, the stronger the traction, typically the well, the stronger the traction, yeah, the stronger they're going to be held to each other. So the stronger, let's say, the hydrogen bond, the stronger the IMF. But how can you figure out? For example, look at these two. You know, yeah. When I look at this, the charge is, you know, this is negative, this is positive. Are there any other factors?
The charge and the distance.
Yeah, the charge and the distance. And the charge and the distance, well, the distance, charge and distance, I started labeling differently in Chem 1A. Any Chem 1A students want to tell me? I want to treat that as a composite. I want to treat both the charge and the distance as one term. And so I called it the charge density. And so we look at the charge density. You know, how concentrated is that charge? How high is that charge here? And so the charge density is going to depend on how big the ion is. So if I have a big anion here, it's going to have a lower charge density. Let's say this is chloride. If I were looking at bromide, bromide is bigger, has the same -1 charge, but is distributed over a larger volume. Okay, so that has a lower charge density. If I look at fluoride, fluoride is smaller than chloride, and so that has a higher charge density. And other things are going to impact the charge density. So a -1 ion versus -2 ion. -2 ion should have a higher charge density. And so what we look at is, you know, when we're looking at these interactions, we're looking at, you know, the charge density, how concentrated is that charge, because the higher the charge density, the greater the attraction is going to be. And so these ion dipoles can be quite strong. In fact, to give you an idea of how strong these ion dipoles are, we can look at Hess's law. This is from chapter 13 here. If we look at Hess's law, whenever we dissolve something in solution, energetically, there are three processes that happen. One, we got to break the solute-solute interactions. So what are we breaking here? We're breaking the lattice. How much energy is that going to cost? A lot. 780 kilojoules per mole. Okay, then we break the, actually there's something else missing here. We got to break the solvent-solvent interaction. When we break the solvent-solvent interaction, that's going to cost us, well, in order to separate, because we got to make room for the ions in solution. All right, so if we make room for the ions in solution, we got to break the water molecules apart to make room. How much energy does that cost us? About
25.
25 kilojoules per mole. And then we form the solute-solvent interaction. And forming the solvent interaction is going to be highly favorable. That's going to stabilize things. And so that should be exothermic. And so when we look at the solution process, you know, we break, and then we form. Okay, when we form here, we're forming the solvated or hydrated. We call these solvated or hydrated ions, and the hydrated sodium ion and the hydrated chloride ion. And so, cost us energy a lot, costs us energy, and gives us energy in return. And when we add up all these steps here, we come out at about break even. And so you might think, wow, you know, 780 kilojoules per mole, that's a lot of energy. And so it doesn't seem like it should dissolve in water, but it does dissolve in water because these hydrated ions are exceptionally stable. These energies of hydration are quite large. Well, it doesn't quite come out break even. It's actually going to cost us a little bit of energy. It's going to cost 5 kcals per mole. And so if it costs us energy, then that means overall we're going from something more stable to something less stable energetically. And so why would we go from something that's more stable to less stable? Because actually it is more stable. Sodium chloride solid and just pure water is more stable than sodium chloride AQ. And so why does this happen? Do you know why this happens? Is because there's one way of thinking about nature, and the driving force in nature is that there are two driving forces in nature that we can think of. One is nature likes to minimize energy and maximize, starts with an E also, entropy. And entropy is a measure of disorder. And so so the reason this happens is because entropy drives it. Okay, so sodium chloride's right kind of at the edge. You know, this is close to break even. Now, if this was energetically favorable, that is, it releases a lot of energy, then no problem. For example, sodium hydroxide. You know, sodium hydroxide, when you dissolve that in water, it's highly exothermic. And so we're going from something less stable to something more stable and getting a lot of energy out of that. Now, do you guys remember the solubility rules? Yeah, well, you know, one of the things that can help you is, you know, because it's easy to forget. It's easy to forget rote memorization, but if you memorize certain patterns or certain trends, it's a lot easier to remember those. And so, do you remember any patterns in the solubility rule table? All right, let me give you, you know why you want to memorize patterns and trends is because that gives you a more powerful tool than just memorizing the table straight up. And so if I said lithium fluoride, what would you expect? Lithium fluoride to be more soluble or less soluble than lithium chloride? It'd be less soluble, and why would it be less soluble? Okay. Well, how about calcium fluoride versus magnesium fluoride? How about sodium chloride versus sodium bromide? Okay. So that's good. Those are types of things you want to think about. And so if you see a pattern, you can do a lot more. Actually, you could do a lot more if rather than looking for a pattern, you could do a lot more if you had some kind of experience. Yeah, 30 years of experience would do good, but you know, why does 30 years of experience do good? It's because, you know what I did a lot of, and what everybody around me did a lot of, was the scientific method. And so I know I asked you to, did we write it down on the board? No. The scientific method that I'm accustomed to and everybody else around me was accustomed to is different than what we have in Petrucci, and it's different than what you guys are taught in biology. And so let me write it here. And so the first thing is we observe. Okay, so observe this. What do you see here? Well, I see just a jumble of numbers, right? And what are these numbers here? Lattice energy. So the Petrucci doesn't have a lattice energy off the chart, so I just took this off the internet. There are plenty of lattice energy charts on the internet. And so what do I see as far as lattice energies go? Well, this is in kilojoules per mole. And so what's on the low end of lattice energies? It looks like around here on the low end. What's the high end? Maybe around 600 to 16,000. You see? That's a pretty big range. And then you look for patterns, you know. Is there something consistent with the low end versus the high end? You know, what makes a very strong lattice? You know, and so this is 16, this is close to 16, these are 3,000, there's 1,000, down to 600. Do you see a pattern there?
The oxygens are higher?
Yeah, earlier in the morning somebody said, you know, there are more oxygens. So the more oxygens you have, the higher the lattice energy. And so in the scientific method, actually, forgot to show this. So in the scientific method, what do? We take our observations, so that's just what we did. And so this is why I look at tables like this. And then we look for patterns and trends. You see that? Okay, then, you know, we look, and this pattern seems pretty consistent. And so when we have a consistent pattern like this, then we want to formulate a law. And what is a law? A law would be like, you know, a consistent pattern. It happened, like the laws of thermodynamics. You know, that pattern. People have been trying to find violations of the law of thermodynamics, but they haven't been successful. Energy is neither created nor destroyed. Well, we have our new law. This is the law of the number of oxygens. The more oxygens we have, the stronger the lattice. Lattice energy. That's our law. Maybe we could even find a mathematical pattern. Like 3 oxygens gives us this many kilojoules. Do you think we'll find it? We try to find a mathematical pattern and see. You know, it's like when you observe the lines in the hydrogen emission spectrum. You have the red, the green, the blue, and the violet. And it doesn't look like those fit a mathematical pattern, but they do. Do you know what that pattern was? Do you know the law of the hydrogen emission spectrum, what it's called? It's called the Rydberg equation. And the Rydberg equation is what we call an empirical law, because all they did was they figured out the math that defines the pattern of light in the hydrogen atom. And we got the Rydberg equation. Do you remember the Rydberg constant? Let me take a side topic here. What was the Rydberg constant? It was like 2.17 something times 10 to the minus, not 20, 10 to the minus 18 joules. 10 to the minus 18, 10 to the minus 19 joules. How much water can you heat up with that? Nothing. I mean, that's zero, right? And so what you have to do is not only do you have to have some kind of idea about numbers, and so this is why we're talking about numbers. You want to get more comfortable with numbers, because if somebody's saying, you know, I got lattice energy at 10 to the minus 18 joules, what would you think? You'd think they're crazy, because, I mean, that's nothing. That's zero. But if somebody said, okay, I got in this emission spectrum a photon of 10 to the minus 19 joules, then would that be something or would that be nothing? If they got a photon of, let's say, 10 to the minus 10 joules, what would you think? A photon of 10 to the minus 10 joules, something or nothing? A photon of 10 to the minus 10 joules, significant or insignificant? For a photon, that is insanely large, 10 to the minus 10 joules. You know, where would it be in the electromagnetic spectrum? It'd be off the charts. And so this is why we need some numbers, because when you do these calculations, pretty soon the numbers blend into each other. Pretty soon it's hard to get a gauge of what the numbers mean. But, you know, if you're going into science, people aren't going to, I say this all the time, but people aren't going to care that you can punch a calculator. You know, anybody can be trained to punch a calculator. People are going to care about, do you know what the numbers mean? Do you know if it's significant or insignificant? Do you know the uncertainties associated with that number? That's what they're going to care about. You know, they want to know what the numbers mean. They don't want to know that you can punch things into a computer or a calculator and get some answer. And so, well, in order to get a better idea of what the numbers mean, we have to memorize some numbers here and there, and then just repeat it because they're easy to forget. And so, don't worry about memorizing everything just yet. But we have the law of oxygens. Now, is there a violation of the law of oxygens? It seems like maybe there is, because if I look at these, magnesium oxide, calcium oxide, strontium oxide, barium oxide, these all have just one oxygen. But when I look at it, these all have one oxygen, but you look at the energies are, well, they're close, but they aren't the same. There are other species that have one oxygen. Sodium oxide. Let's scroll down here. I don't know if sodium oxide is on this chart. Yeah, it is. You look at sodium oxide here. Now it's dropped below 3,000. You know, so there's more to it than the law of oxygen, because the law of oxygens doesn't quite do it. Right? And so what we want to do, well, we want to come up with a better law, a more refined law. And once we get a more refined law, well, the law just doesn't quite do it, because that's empirical. You know, it doesn't really explain what's happening, right? And most laws are just empirical. They're just mathematical equations that fit the phenomena. But we don't want that. We want a little bit more. What's the more that we want? And so the next step in the scientific method is the hypothesis, because you got to figure out, why is it that when you have more oxygens, the lattice energy seems to go up? You know? It's not just a simple rule, but there's got to be more. And what a hypothesis is, can somebody define it for me? A hypothesis is a fundamental, let's see how much time, explanation, you know, or description. Well, scientists like to just describe nature. You know, nature is the way it is, and so you want to get as deep of a description as possible of what or how it works. Well, anyway, a fundamental explanation, and a hypothesis is tentative. You know, tentatively, I'm going to say that it seems to work because why? Well, we start looking at it deeper and deeper and trying to get a better and better picture of it, and then what we see is that, well, what holds the lattice together are ionic bonds. And ionic bonds are attractions between positive ions and negative ions. And so the pattern that I see is that this. the higher the charge density on the cations and the anions, the stronger the lattice. And so here, look at 3 plus versus 2 plus versus 1 plus. And so if I go 1 plus cations, low, 2 plus is stronger, and 3 plus are the strongest. Where have you seen that pattern before? You've seen that pattern before in the solubility rules. What are insoluble? The insoluble species have strong lattices. And so what would you expect that to be? The nitrates and the acetates? Nitrates is NO3 minus, acetate is C2H3O2 minus, or the carbonates, and the phosphates, and the chromates. The carbonates are 2 minus, phosphates 3 minus, chromates are 2 minus. So do you expect the higher charged species to be harder to break apart, or the lower charged species? The higher charged are going to be harder to break apart. So the phosphates, carbonates, and chromates are all insoluble except when they're attached to group 1. Well, group 1 has low charge density. Those are just +1. And ammonium is a big polyatomic ion with just a +1 charge. And so that +1 charge is spread out over a pretty big volume. And so, whereas the higher the charge, the stronger the attraction. So we see that same pattern here. And then we see it here in this series here, because if we compare magnesium, magnesium's 2 plus, barium's 2 plus, but what's the difference? Magnesium has a higher charge density, even though it has the exact same charge. Why does magnesium have a higher charge density than barium? Because it's a lot smaller. And so, since it has a higher charge density, this ionic bond is going to be stronger. So magnesium oxide, is magnesium oxide soluble in water? No, you cannot dissolve magnesium oxide in water. Why? Look at that lattice energy, 3,800 kilojoules per mole. Do you think that's going to be compensated by solvating or hydrating the ions? No, this is too energetically unfavorable. Even entropy isn't going to be able to overcome this. And so magnesium oxide, in fact, the oxides typically are insoluble. Why? Because of the high charge, except for group 1 and ammonium oxide. So group 1 would be like sodium oxide. Sodium oxide is actually soluble. All right, now let's look at this. These are all the same cation here, lithium, but let's look at the anions. We go from iodide, bromide, chloride, fluoride. Which one's going to have the highest lattice energy? Fluoride. Why? It's the smallest. And so it's going to have the highest charge density of negative charge. Or the distance. You can think of it in Coulomb's law, charge and distance. And so it's the same thing. And so you can see lithium fluoride, lattice energy, 1036. Chloride, bromide, and iodide are successively smaller. And so there are a lot more exceptions because fluoride, chlorides, bromides, and iodides are soluble except for silver, right, lead 2, and mercury 1. There are a lot more exceptions for fluoride. If you added fluoride to that list, you have to memorize a bunch more for the except column. Okay, so then we hypothesize, the lattice energy has to do with the strength of the ionic bond. The strength of the ionic bond has to do with the attraction between the charge.
I kind of forgot what entropy is.
Oh, don't worry about entropy. Entropy was just briefly talked about in chapter 13, but we're going to spend a huge amount of time talking about it this semester.
Okay.
So in Chem 1A, you learn about qualitative driving forces, like these things. A driving force is what pushes the reaction along. So precipitation, neutralization, or gas formation. Those are driving forces for certain reactions. In Chem 1B, what we're going to do is we're going to quantitatively calculate the driving force for chemical reactions. And so we aren't just going to predict. We're going to put some numbers on chemical reactions to see what the force pushing it forward is. And there we need entropy and the second law of thermodynamics. We'll talk about that a lot. So don't worry about entropy now.
Wasn't chloride like an exception
Yeah, you're right. Chlorides, there are always going to be exceptions. And so the exception you're thinking about has to do with chloride versus water. Yeah. That has to do with chloride is I don't know. Did you guys cover? Maybe a lot of you didn't cover this, but did you know what's a better reducing agent, chloride or water? According to the chart, water. But that's the exception. Chloride is easier. But we'll talk more about that because that's something I talked about, but it's not in the book. Oh, and we're going to repeat that because we're going to see exact same thing in electrochem in chapter 20. And so we're going to spend a lot more time with redox. All right, now this is tricky because if this were melting points, it'd be easy. Because melting points, you're just breaking the bonds, melting it. But this is not just breaking the bonds, we also have to hydrate the ions. And so this was the exception that I was talking about earlier. And this is an exception where hydrated ions come in. And let me just briefly talk about this, and then we'll go on the break. Do you remember ionization energies? The bigger the atom, the easier to ionize or the harder? The easier it is to pluck the electron. And so let's compare lithium. Lithium is small, potassium is big. Which one's easier to ionize? Potassium is easier to ionize. So which one should be a better reducing agent? Reducing agents give up their electrons. Should potassium be a better reducer or lithium? Potassium should be. But what's at the top of the chart, the activity series? Lithium is at the top of the chart. Why is lithium more active than potassium? Potassium should be more active because it's bigger, it can lose its electron easier. And so does somebody have an answer for that? In fact, when you look at it, when you look at potassium reacts in water. I did this in the summer. I forgot to do this last semester. I'll do it again this semester. But when you throw a chunk of potassium in water, it ignites in a big flame. Lithium, you throw a chunk of lithium in water, it just slowly reacts. And so when you visually watch the reaction, lithium appears to be a lot less reactive than potassium, but lithium's at the top of the chart. Do you know why? The reason why is there are two processes happening. One is losing the electron. This is why potassium reacts so violently, because it's easier to lose the electron in potassium. But two is hydration. Potassium ions are kind of chunky and big, and therefore you have to break apart a lot more waters to fit that potassium ion there. Also, when you hydrate big ions, the interaction isn't as strong because the charge density is a lot lower. And so what happens in the long run is lithium releases more energy to the environment because when you hydrate lithium ions are tiny, and that hydration, ion dipole attraction, is very strong. And so in the long run, it releases more energy. In the short run, it's less reactive. And so it has to do with the stability of the products, not the reactivity of the reactants. In fact, we're going to be doing a lot of reactions this semester. And when we do reactions, we always got to think, how reactive are the reactants, how stable are the products? And that's going to tell us, the driving force for reactions. So we're going to be looking at these types of questions a lot this semester. But that's an aside. Size, because of its size, right. We don't have the activity series in this chart. Let me just. Do you guys remember that? The activity series is more like in Chem 4. What's at the top of the chart? Lithium. And where's potassium? Potassium's the number 2. No, potassium should be number 1, or rubidium actually should be higher because rubidium is even bigger than potassium, but rubidium's not on this one. Most activity series only have lithium, potassium. Rubidium's not as common. And well, anyway, and sodium. Look at where sodium is. Way down here. And this has a lot to do with the hydrated ions. And all right, so let's take a break and then we'll start up again in 10 minutes or so.